Hi, this is Hikaru Nakatani from Nagoya University, Japan. Today, I would like to give you a presentation titled Cross-Lingual Voice Conversion using a cyclic variational autoencoder and a wavenet vocoder. Voice conversion is the process of converting the paralinguistic and non-linguistic information in its source or input speech into those of a target speaker while retaining the linguistic information. For example, this makes it possible to convert a speaker's voice into the voice of a famous cartoon character or another specific person. And some real-life applications for overcoming a speaker's physical constraints can also be possible, such as providing more natural-sounding vocal expression and vocalization support for people with speech impairments, such as dysphonia. Parallel VC methods have been widely studied in the existing VC frameworks, but the performance of non-parallel learning-based methods have also been dramatically improved in recent years thanks to the deep learning techniques. Cross-lingual VC specifically refers to the situation where the source and the target speakers are speaking different languages. For example, you can convert this German speaker's voice.
Das Gericht stützte sich in seinem Urteil im Wesentlichen auf Aussagen der Gutachter.
Into this Japanese speaker's voice.
あらゆる現実をすべて自分の方へねじ曲げたのだ。Das Gericht stützte sich in seinem Urteil im Wesentlichen auf Aussagen der Gutachter.
This technique can be applied to various applications, such as pronunciation practice of learning foreign languages, dubbing a movie with an original actor's voice, personalizing interpreted speech, and personalizing translated speech. Various VC methods have been proposed to realize cross-lingual VC until now, especially parallel VC methods which use the same language and the same utterances datasets have been extensively studied. But in order to prepare such dataset, there is a method using bilingual speakers, but it is not realistic for practical use since the number of bilingual speakers is fairly limited. Another popular approach is the use of whatever prior information is available when developing the conversion model. There is a method using phoneme information, but this approach requires a pre-trained phoneme recognizer. So in our proposed methods, we apply cyclic variational autoencoder to cross-lingual VC. This is one of the non-parallel learning-based methods, which does not require neither parallel data nor pre-trained phoneme recognizer. In addition, in our second proposed method, we apply wavenet vocoder in the waveform generation process of cycle VAE VC to improve overall conversion quality. In the VC based on the variational autoencoder, the encoder network extracts the speaker-independent latent features by using the speech features of the input, and the decoder network generates its speech features with the desired speaker characteristics from latent features, along with the given speaker code. On the other hand, in the VC based on cycle VAE, the input speech features are once converted into another speaker's speech features, and converted into the input speech features again. As a result, it has been confirmed that cycle VAE achieves higher conversion accuracy than vanilla VAE when the source speaker and the target speaker speak the same language. But in the previous cycle VAE research, BERL was used in the speech waveform generation phase. This is a parametric vocoder, which is only based on extremely simplified assumptions of the speech generation process and causes significant degradation in the conversion quality. To tackle this problem, neural vocoders have been widely used in the waveform generation phase in recent years. Wavenet vocoder is one of the autoregressive deep speech waveform generation models, which is possible to learn the generation process from speech features to waveforms in a data-driven manner. Thanks to this nature, wavenet vocoder is possible to generate a natural sounding speech almost identical to human speech when the sufficient amount of speech data are given. But generally, wavenet vocoder requires quite a large amount of speech data to obtain reasonable quality of speech samples. In general, developing a speaker-dependent wavenet vocoder requires about an hour of speech data from the target speaker. So in many studies, a multi-speaker model that uses data of multi-speaker is developed firstly, and then fine-tuning is performed only using the data of the target speaker. But there are some problems with fine-tuning the wavenet vocoder. When fine-tuning is performed using natural features extracted directly from the speaker's speech data, it is effective when generating speech waveform from natural features. But in the case of VC, The characteristics of the natural features used during the training phase and the converted features used in the conversion phase differ, so it causes a significant quality degradation. In addition, since the converted features have a different temporal structure from that of the target speaker, it is difficult to directly use the converted features for fine-tuning. One way to address this issue is to use the self-reconstructed features generated from a conversion model. In the previous research, cyclically converted features are used for fine-tuning. These kind of self-reconstructed features have an identical temporal structure to the original target waveforms, so they can be easily directly used for wavenet vocoder training. It is also known that the quality of these features are close to the converted features. In addition, similar features can be generated by the conversion model using VAE as well. In previous research, it has been confirmed that the features once made latent variables by the encoder and reconstructed by the decoder have similar quality to the converted features and effective for fine-tuning. Cycle VAE is also capable of generating these kind of features, and they have the same temporal structure to the target speech. So in this research, we hypothesize that they are also effective for fine-tuning wavenet vocoder, as in the case of VAE. Okay, let me elaborate the learning flow of the entire model of the second proposed methods. Firstly, we developed cycle VAE, including the source speaker, target speaker, and 24 additional speakers. After that, we fine-tuned the pre-trained multiple speaker wavenet vocoder model, including the target speaker, with the reconstructed feature of the additional speakers and the target speaker, and the cyclically reconstructed feature of the target speaker. Here, the reconstructed feature of the additional speakers are expected to act as regularizing data to prevent the model from overfitting. In addition, we conduct data augmentation for cyclically reconstructed features to improve the conversion accuracy. Then, we further fine-tune the first fine-tuned wavenet vocoder model only with the self-reconstructed features of target speaker. Finally, we obtain the converted waveform by inputting the converted features to the fine-tuned wavenet vocoder. For the experiments, we prepared 3 different types of VC methods, including baseline methods. Baseline is a method based on parallel learning using recurrent neural network, using 50 English utterances of an English speaker and 50 Japanese accented English utterances of a Japanese speaker. Both proposed methods use 50 English utterances of English speaker, 50 Japanese utterances of Japanese speaker, and 350 English utterances of 24 additional English speakers for learning. In terms of vocoder, we use World for baseline and cycle VAE. This is the results of the experiment. As you can see here, our proposed methods outperform the baseline system in terms of naturalness and speaker similarity. I would like to play the actual speech samples with each method here. The first one is the English speech of the source English speaker.
This is a library that would do credit to more than one continental palace.
The next one is the converted speech of the baseline methods based on parallel learning.
This is a library that would do credit to more than one continental palace.
The next one is the converted speech of the first proposed methods.
This is a library that would do credit to more than one continental palace.
The next one is the converted speech of the second proposed methods.
This is a library that would do credit to more than one continental palace.
And the next one is the English speech of the target Japanese speaker.
This is a library that would do credit to more than one continental palace.
And the last one is the Japanese accented English speech of the target Japanese speaker.
This is a library that would do credit to more than one continental palace.
So in this research, we applied cycle VAE to crosslink a VC scenario and confirmed the capability of it. More specifically, we confirmed that our proposed methods outperform the conventional methods in terms of naturalness and speaker similarity of the converted speech. We achieved further improvements in performance by using a wavenet vocoder in the waveform generation process. As future work, we plan to explore better fine-tuning methods and apply them to real-life applications. Thank you.